Most, if not all of us, have seen fireworks on the 4th of July and neon signs brightening the city streets. But how is the light emitted? And why do different chemicals give off different colors? To answer these questions, we must study electron movement within the electron cloud and understand the properties of light. An interesting property of light is that it can behave as either waves or particles, depending on the circumstances. This is called the wave-particle duality of light. The fact that light can act as particles and can transfer all of its energy to a different particle, such as an electron, was important in the development of the quantum mechanical model of the atom, or the modern atomic theory. In this class, we will mainly focus on light behaving as a wave. Light is composed of many waves of different wavelengths, ranging from large wavelengths, kilometers long, to very small wavelengths that are only picometers in length. When describing the length of a wave, we usually use the units meters or nanometers. One wavelength is defined as the length between two adjacent crests, but you can use any two corresponding adjacent points as shown in the diagram. Wavelength is represented by the Greek letter lambda, which looks kind of like an upside-down Y. Although we typically think of light as the energy that enables us to see, visible light is just a very small portion of what is called the electromagnetic spectrum. Visible light includes the colors of the rainbow, and the wavelengths range from approximately 700 nanometers to 400 nanometers. One way to remember the order of visible light from longest wavelength to shortest wavelength is to remember Roy G. Biv. The color red is the longest wavelength, while violet is the shortest wavelength. We see colors when certain wavelengths are reflected off of an object. If all the colors are reflected, the object appears to be white. If all the colors are absorbed, the object appears to be black. The electromagnetic or EM spectrum includes all the characteristic wavelengths of electromagnetic radiation, or a portion thereof, that are emitted or absorbed by an object, molecule, or atom. You have probably heard of most of these types of electromagnetic radiation. Radio waves carry the songs and information we listen to on the radio. The number of the radio station, for example 102.1, refers to the frequency of the wave, which we will discuss later. Microwaves are used in a microwave to heat food and drinks. Infrared radiation is emitted by heat lamps to help keep reptiles and other animals warm, and by your TV remote control. Certain types of thermal imaging devices capture infrared radiation emitted by objects so you can see them at night. Our eyes detect light in the visible light range. Red light, which has the longest wavelength, is just after infrared radiation. Violet light, which has the shortest wavelength in the visible range, is just before ultraviolet light. Ultraviolet light is used in tanning beds and by forensic scientists to detect blood and other bodily fluids at a crime scene. X-rays, of course, are used to detect broken bones. Gamma rays are emitted during nuclear reactions, which we will study later this year. All light, meaning all parts of the electromagnetic spectrum, travel at the same speed in a vacuum. This is the most accurately known constant in the world. The speed of light, which is 3.00 times 10 to the 8th meters per second, is represented by a lowercase c. The frequency of a wavelength refers to the number of wave crests which pass through a given point in 1 second. Frequency is represented by the Greek letter nu, or the lowercase letter f, and the units are either cycles per second, reciprocal seconds, or hertz. In a vacuum, all light travels at the same speed, so frequency is only determined by the wavelength of the wave. Watch the waves as they leave the screen. Notice that more wavelengths of the purple light leave the page than wavelengths of red light. This illustrates an important property of light. The shorter the wavelength, the higher the frequency. Wavelength and frequency are inversely related, which means as one increases, the other decreases. Light also has energy. When light acts as a particle, it can transfer all of its energy to another particle, such as an electron. Energy is directly related to frequency, but indirectly related to wavelength. This means that long wavelengths, which have a low frequency, also have a lower amount of energy. The low energy end of the spectrum includes radio waves, microwaves, and infrared radiation. Electromagnetic radiation with short wavelengths, which have a high frequency, have a higher amount of energy, which is why they can cause significant damage to your skin and DNA. The high energy end of the spectrum includes ultraviolet light, X-rays, and gamma rays. Pause the video and try these problems which are in your notes. When you are ready, restart the video for the answers. The answer to number 1 is a longer wavelength because the wavelength and frequency are inversely related. That is, as one increases, the other decreases. The answer to 2A is red. Remember, the colors in order of longest wavelength to shortest wavelength are red, orange, yellow, green, blue, indigo, and violet. The answer to 2B is green because green light has the shortest wavelength and therefore the highest frequency. The answer to 2C is green because green light has the shortest wavelength and therefore the most amount of energy. The next video for this unit will explain how to solve problems using the energy, wavelength, and frequency of light. Thanks for watching.